All right, everyone. In today's video, I want to talk to you about the topic of heuristics, and we're going to do some heuristic analysis and see why heuristics matter. Okay, so heuristics basically is a way to analyze a problem. This is an approach that is a little bit different from a normal type of strategy for solving the problem because we rely based on practical experience-based techniques to find solutions that are not guaranteed to be optimal, but in most cases are very, very, very good and guaranteed to be basically good enough. So if good enough is good enough for you, then you should consider this approach. Okay, so some people need absolute precision. Some problems are very complex and very time-consuming to solve, right? So if you need an answer with 15 decimal places of precision to the right side of the decimal, then a heuristic approach is probably not right for you. But if you want to get a very, very, very close approximation for a solution that's good enough, then you should consider using heuristics because in many cases, these are magnitudes faster than a brute force approach to solving the same problem. Okay, so this method is used in many situations, especially finding when an exact solution is not feasible due to time constraints or computational resource constraints. This is going to be a quick approximate answer that's very accurate. Again, not exactly precise, but very, very close. And if the problem is extremely complex and very, very difficult to solve, a brute force method might just might not do it. It might fall down. It might take a lot of time. It might crash your system, and you would have to resort to a heuristic approach. So I've seen in the past where people use brute force methods to solve problems, and it could take hours, it could take days, even weeks. With a heuristic approach, the same problem could probably be solved in a tiny fraction of the time, maybe less than an hour, maybe just a few minutes. Okay, so let's look at some examples here. We have the classic traveling salesperson problem. This is where a person starts at one city, returns to the starting city. Okay, that's going to be their home base. That's the assumption. A non-heuristic approach would create an exact solution or find an exact solution using a brute force method, and it would generate all permutations of all cities and calculate the total distance and the total time traveled to each city. Each city is considered a permutation. Okay, a heuristic approach would find the nearest neighbor heuristic. Okay, like a KNN, like a K nearest neighbor. Whoops, heuristic, and we will start at any city and end at any starting city, and each step along the way is going to touch on the nearest unvisited city, right? So once you go to one city one time, it's off the list. You don't have to go back to that city, and you're not going to crisscross back and forth across the United States. If you have to travel to many cities in the US, you'll go to one and then another, probably in a loop, maybe like a kind of a zigzag fashion. But if that happens, it has to be the shortest route and the shortest time to visit every city, okay? So typically it's circular or curvilinear. It's not going to be a linear back and forth zigzag pattern. So let's look at an example here. We have 5 cities here. We're going to start in St. Louis. We are going to go to New York City, then Miami, Los Angeles, Portland, and then Boise. Whoops, I misspoke. There's actually 6, okay? So we have 6 cities here. And we have the latitude and longitude coordinates for each one. Okay, so we are going to calculate the haversine distance. This is the geological distance between coordinate 1 and coordinate 2. This would be coordinate 1, lat long for 1 and lat long for 2. So this would be the starting lat long and then the ending lat long, okay? And I've talked about haversine distance in some of my other videos. You can check those out. This is how we find the distance between 2 places on the curved surface of the Earth, okay? So we're going to look at 2 approaches, a brute force method, where we list all the cities here. We look at the keys and the cities. This is basically the index of this data frame right here, or this dictionary. I'm sorry, this is a dictionary. You have a key and a value separated by a colon. You can tell it's a dictionary because of the key value pairs. We're going to go through all of the items in those keys, okay? And the alternative is to use a nearest neighbor approach. We have the starting city right here, all the cities in the list. Again, we go through all the key value pairs in that dictionary, and we come up with a solution. So I'm going to share this code with you. We don't have to get into all the details and all the nuances of what the code does right here. You'll have the code so you can explore that at your leisure. You'll have unlimited time to do that when I post the video. I will share the code with you guys. Start city. Okay, so did I have to? Okay, let's just do this. Start city. I forgot something here. Start city. Okay, put that in quotes. It can be single quote or double quote, doesn't matter. Let me see here. Control enter. Yeah, so it's missing a start city. Not sure why that fell off, but okay, here we go. So we have. Let me do this one more time because I'm actually getting a 0 for the nearest neighbor approach. It's so fast it didn't even register to 4. Let me make this a little bit bigger here. Okay, sorry about that. It's so fast now I can't even actually record the time that it takes to do the calculation. Let me try to up that a little bit to more precision. 0.0 seconds. Okay. Let me do this. Sorry, 0.15. The heuristic here is just too fast. Okay, finally we got something that we can record. I can't divide by 0, so I had to see some kind of time to complete the heuristic here. So let me calculate the actual time to do this calculation here. You can never divide by 0, right? It's a mathematical impossibility. So let me go down here and do this, and we'll get the actual time to complete. We'll do end divided by beginning minus 1. Whoops, divide by A2 minus 1. 48 times. Okay, so we got our answer. 48 times. This is 48 times faster. So that is pretty huge, guys. This heuristic performed 48 times faster than the brute force method. I did this yesterday. It's 35.2, 48 times. 48 times faster. So it's probably running some calculations in the background. It slowed down the CPU because it has to share its processing with this and with some other things. Now there's nothing running in the background. So the calculations can be focused just on this task right here. So the brute force method starts in St. Louis, goes to New York, Miami, Los Angeles, Portland, Boise, Idaho, and back to St. Louis. The nearest neighbor heuristic approach did the same exact task, right? And the total distance is 11,039 kilometers. Total distance here is 11,318. So we traveled a little bit further here, but the time to do the calculation was much less. So in reality, we would probably do the calculation using a heuristic and maybe do the actual route planning using a brute force method, because this is about 300 change, about 300 kilometers shorter, right? So it's less distance for the traveling salesperson when they're driving around or, moving from point A to point B. So this path is a little bit shorter, but the computation time is magnitudes faster, right? 48 times faster to do the nearest neighbor brute force method, right? So 48 times could be substantial. If this brute force method takes, I don't know, I'm just saying an hour, this could take just over a minute. If this takes 48 hours to complete, this would be done in 1 hour, right? So if you can do your job in 48 hours versus 1 hour, which would you pick? I would pick the 1 hour, okay? I've worked in places where people will literally take 48 hours to do something. They get the results. It doesn't match your expectations. They have to rerun the analysis. They burn through 2 more days. That's 48 hours. Again, the analysis doesn't make sense. Now you're at the end of the week. You're coming up on Friday, right? And you're rerunning the analysis. Probably your time is overlapping into Saturday. Now you have to work on the weekend because you couldn't get the results that you wanted because the computation time is too long and the processor just isn't cutting through it in a feasible, realistic amount of time. This guy over here can run 10 experiments in 1 day and be done with each and get the results and report back to the boss. This guy over here is just running 3 analysis. It's taking him the entire week. He still doesn't have what he needs. So which approach would you pick? I would go with the nearest neighbor right here. Okay, it's done 48 times faster. Let's look at another example here. This is job scheduling on different machines. Let's say we have 10 different jobs and we have 2 machines. And this job can be anything. Baking bread, making donuts. It can be cooking food for customers. You could be making tables. You could be making chairs. Any kind of process that takes time. And you have machines. This could be burners in the kitchen if you're cooking. This can be a manufacturing facility. It doesn't matter, right? You have 10 jobs, 2 machines. So you can allocate about 5 jobs per machine. But if some jobs run faster, maybe you can put 6 jobs on one machine and 4 in another, right? We don't know exactly what the most efficient method is, but we'll let the algorithm determine that for us. So we're, again, doing the brute force method and heuristic method and looking at the outcome of both. Okay, and in my notes here, I have heuristic approach, the longest processing time, heuristic to assign jobs in descending order of their processing time. And the non-heuristic approach is try all permutations of job assignments. So this takes exponentially longer than this approach, right? You look at the longest job and assign that to the machine that has the most resources. If the job is done pretty quick, 10 minutes for job 1, 10 for 2, 15 for 3, 10 for 4, and then I'm just saying like, I don't know, 30 minutes for the 5th job. You would get those in all descending order, get the longest running job, assign that to one machine, assign the shorter jobs to the other machine, so you can cut through it pretty quick and pretty easy. Okay, I need a sip of coffee. It's still early here. I have to wake up. So we have the brute force method. There's going to be 28 tasks done completely, and here the heuristic approach has 28 also. Here the brute force method says it takes 35.9 seconds to complete. So let's record that, 35.9, and this takes 0.00107 time to complete. Let's look at the boost and productivity minus 1. Okay, division happens first. So 35.09. Let me get these metrics over here, and we have a division. I'm updating my notes. When I did this yesterday, I had a couple tasks running in the background, so I think that slowed things down or changed the variability of the time to completion just a little bit. Now there's nothing running, so this can be pretty fast. Wow, this is a huge boost. Okay, so let me get that, and we don't need decimal places. I think the solution is pretty obvious here. So instead of taking 35 seconds, this heuristic finished in 0.001, so 1/100th of a second. And this actually is 32,793 times faster, okay? That is huge, guys. If you can't comprehend that, just take a minute, ponder it, take a lap around your living room or your den, your office, wherever you are, and think about how much productivity gain that is. 32,793 times faster to do the heuristic approach, came up with the same answer, and the brute force method was slow and cumbersome because that's to look at every single permutation of every combination. That comes from these tasks over here, right? We have 10 jobs to run on 2 machines. The heuristic approach looks at the longest running time and says, okay, we'll assign that to one machine, looks at the next longest, and tries to assign tasks based on the availability of the machine. So if one task will take 10 hours, all the other 9 tasks take maybe half hour each. You can finish in half the time. That would be about 4.5 hours, right? And machine 1 is already done before machine 2, or whatever the task is. I don't have all the details here, but you can see overall, the heuristic approach is much, much, much faster than the brute force approach, okay? So if you have to do this iteration over and over, obviously you would pick this, right? The outcome is the same, 28 and 28. But the time to complete the task is a tiny fraction, right? 32,000 times faster. So here's another example of vehicle routing problem. We have an objective function that we're trying to solve. Again, the distance matrix. This could be meters or feet. It's nondescript, so we don't have to worry about the actual distance metric, but we have to go from 0 to 10 to 20, 30, 40. In reality, this might be longitude, latitude coordinates, right? If we're traveling, like in the traveling salesperson problem, this is a lat long coordinate for this city. This is a lat long coordinate for this city, another, right? So we are just saying distances, but this easily could be latitude, longitude coordinates, and we can calculate the distance using the Haversine method, like we saw before. Okay, I just have a distance matrix, just keeping it simple and keeping it just pretty bare bones at this point. So we have the total distance metric here, the brute force. UDF, this is the user-defined function, starting with the def right here. And the def here is generate partitions. And we are going to use all the partitions, right, or all the permutations. So one and another, every single combination or permutation. A permutation is when the order matters, and a combination when the order doesn't matter, right? If I Google that real quick, permutations versus combinations. Okay, we can go here. Mr. Google picked up the first thing it found right here. It's displaying that the order of the items matter. Okay, so permutation, order matters, combination, order does not matter. So in a permutation, you have fewer outcomes. In combinations, the order doesn't matter. right? It can be any combination of numbers, right, to create that combination. I always thought that was funny because a permutation is really a combination lock. It's called a combination lock if you lock up your bike or motorcycle or scooter or whatever that thing is that you ride. It's actually a permutation lock. I think it was mistaken or mislabeled originally, and the name just stuck. It's called a combination lock, but think about it. It's actually a permutation lock because the order that you put those numbers into your lock matters. So there's a little bit of trivia for you. So we have the brute force method and heuristic method down here, and we're going to go ahead and run it. And this problem, again, looks at the delivery time to get goods to customers from a centralized location, a centralized depot, using multiple vehicles while minimizing the total distance traveled. Okay, so now it's a little bit different from the traveling salesperson problem where you have just one person traveling around. Now you have multiple vehicles traveling around, and each vehicle has a capacity and customer demand must be fulfilled in a certain time frame. Okay, so there's a couple of constraints or a couple of requirements. Again, we have the start time, the brute force total time, brute force total distance, and then the end time, okay, or brute force calculation, total distance, end time. Again, we're doing this 1,000 times to get a sample of distributions of how long this is going to take. We have the start time, the root heuristic, and the end time. Okay, so let me run this. Let me run this guy, and let's see what the outcome is. So it's done pretty fast. This one is extremely fast here. So 0.00476 time to completion. Let me record that. And this one took that long, equals that, divided by that, minus 1, 22.8. Okay, so 22.8 times faster. So let me record that just so we have that over here and get that over there. Make it look nice. Okay, and we have what? 22. Okay, 22 times. So I did this yesterday, got 300. I was running probably nothing at that point because all the resources were dedicated to this. Or sorry, it's probably running nothing. Maybe there's some job running in the background, some who knows what is running on this computer. There's always kinds of Windows processing, scanning, virus scanners and stuff. So this ran a little bit slower, but still the brute force method took 22 times longer than the heuristic method. And the heuristic came up with this pattern 1 and 3, 2 and 4. That's the pattern that we're going to go with. And then the brute force method came up with 0, 1, 2, 3, 4, and 0 again. And then the total distance traveled is 110. Again, we don't have the metrics. This could be miles. This could be kilometers. Here, the heuristic is only 65, so it's much shorter, and it finished faster. So here's a win-win. So it's only 22 times faster. For the heuristic here, it is 3,793 times faster, which is pretty amazing. But the heuristic actually found a faster route. This is 110 kilometers. This is 65 kilometers that we have to travel, or again, it could be miles. The metric is not descriptive of miles or meters. We don't know. Miles or kilometers, we don't know what it is. But this number is definitely bigger than this number. So the distance traveled is further, and the time to complete is actually longer, right? So you get a shorter, more efficient route, and it takes longer to come up with that solution. Here we have a faster route, and it took 1/22 of the time to come up with that solution. So let's look at another similar type of problem. We have capacity limitations, another vehicle routing problem, VSP. So now we have number of customers 5, and we have the demands for each customer. We have the distance matrix like before, the demand for each customer, and then the vehicle capacity. So now we have another constraint that we didn't have in the last problem, but this means there are limitations to how much each vehicle can carry. This could be a delivery truck, maybe bread delivering baked bread or donuts or croissants or whatever to a bakery, right? Maybe it's made in a baking factory and it's delivered to the bakery for sales. Maybe it's an Amazon delivery truck. Maybe it's UPS, FedEx, whatever it is. It doesn't matter. But the vehicle capacity is 30 crates, 30 cartons, 30 boxes, 30 items that it can carry, whatever that capacity is. There's a limitation. In the last example, we didn't have this constraint, which isn't necessarily realistic because vehicles can't carry everything, right? There is a limitation. So let's impose a constraint here and then see what this tool can come up with. So we have calculate total distance. And then we have the nearest neighbor. Okay, so we have the function to calculate distance of the route and the nearest neighbor approach. This is going to be our heuristic down here. And then this is the brute force method. So again, we use the distance matrix, the overall demands, and vehicle capacity. Those are the three constraints that we're dealing with. So let's run it and see what the algorithm comes up with. Control Enter to run. And did it actually run? That was fast. Yes, it did. Okay. And and then we see the brute force method came up with these routes: 0 to 2, 0 to 4, 0, 3, 1, and then 0, 1, 2, 0, 3, 0, 4. So you can see we're hitting all the routes, but we're hitting them in a different order. Again, the time and the distance traveled is longer here. The time and distance traveled is shorter, and heuristic approach calculated in less time than the brute force approach, right? That's exactly what we would expect. I think we've determined that at this point. Let me get this right here and the full precision, and we'll see how many times faster this guy is. Equals that divided by that minus 1 to make the percent here. And let me calculate that or convert that to a numeric. That's a little bit easier to deal with, so it's not scientific notation. And we get 9.82. Okay, so 9.82 times faster. So a little slower, but still pretty impressive. 9.82 times. If this takes normally 1 hour to complete and you can do it 9 times faster, now you're done in 1 hour. What was that thing? 9.2, 9.82. Okay. Do this, right? 9.82. So if it takes 9 hours to complete and your heuristic can do it in 1 hour and the results don't really meet your expectations, you can run this process multiple times per day, at least 8 times per day. And you're probably going to be at the end of the day. Hopefully you have a good run and good outcome, but you could be done for the day. Show your results to your boss and you're done. If this guy runs this for 9 hours and results look a little bit wacky doodle and something doesn't jive and it just looks kind of weird, now you have to explain to your boss, well, we have no results. We burned through an entire day. We could try it again tomorrow. So maybe tomorrow you don't get the results and you have to try the day after. Now you're through half the week. And maybe you still don't have the results that you expect because you have to wait 9.82 hours for this task to complete. Over here, this heuristic is on 1 hour. You can do multiple tasks per day. That's the overall benefit, right? So just to summarize, heuristics involve simplifying assumptions. We ignore less critical parts of the problem and focus on the key factors. This problem has to be solved quickly and efficiently. We're going to get a very good solution. Good enough is good enough. It's not precise. It's not absolutely perfect. But I'll tell you, in the business world, especially in Wall Street, if you're close, it's good enough, guys. If you're that close and you can do something quickly and easily, that's good enough 99.99% of the time. You don't need absolute precision, okay? If you get down to pennies, that's fine. You don't need to determine the price of a bond or a stock or an ETF or a portfolio of stocks with 15 decimal places of precision. That just doesn't make any sense, right? So heuristics are based on rule-based decisions, right? We have predefined rules or patterns that guide us towards a solution. Pick the nearest neighbor. We saw an example of that. And iterative refinement, repeatedly improving the solution by applying a heuristic rule over and over until you get your desired solution. So applications of heuristics are far-reaching optimization problems, things like supply chain demand, supply chain optimization. Heuristics are great for that. Search algorithms, data science and artificial intelligence, and cybersecurity. Heuristics show up big time in the cybersecurity space, right? So they're very useful there too. So that's pretty much it, guys. Please hit the subscribe button and you will be notified of all the new videos that drop. I try to do 1 per day. If I can't get 1 every single day, I try to do 2 the next day. If I can't do 2, I try to bundle it up and do 3 by the 3rd day. I try to do about, on average, 1 video per day for 365 days. That's my goal. I started on August 8th, 2024. Now it's January 28th, 2025, and I'm about 170 videos into it. I think we're 172 days into this challenge. So I'm about on par. I have to make a couple more videos to catch up, but pretty close. That's your heuristic, okay? So thanks for your time. Enjoy the rest of your day. I'll see you in the next video. Bye.